Hello, everybody. This video is going to talk about the last gas law we have to study. We've already talked about Boyle's law, Charles' law, Gay-Lussac's law, and this law is called the ideal gas law, and it's going to incorporate a variable that we did not work with in the previous gas laws. This one is going to incorporate the amount of gas or moles. And as you know from the previous work we did with the gas laws and the problems we worked on, the moles or the amount of gas was held constant. Well, that is no longer going to be the case when we use the ideal gas law. The other gas laws, including the combined gas law, also involve two separate conditions. We calculated what would the volume be if we change the volume to this and the temperature changes and so on. This law allows us to calculate the variables without having to have two different separate conditions. So let's get started. The ideal gas law shows a relationship between the pressure, volume, moles, and temperature of a gas. It was determined that the pressure and volume of a gas sample are related to the moles and temperature by a constant. This constant is referred to as the ideal gas constant, and it's abbreviated with the uppercase R. So to show this mathematically, we have a new equation right here. Please notice PV equals nRT. This shows that the product of the pressure times the volume is going to be related to the moles times T by the ideal gas constant R. So in the equation here, P is pressure, V is volume, N is moles, R is a gas constant, and T is a temperature. So you have to recall that in all gas laws, temperature is always Kelvin. Some of you on the last test forgot that, unfortunately, and you lost some points. But anytime working on the gas law, you've got to make sure you're expressing the temperature in Kelvin. Since R is called the gas constant, that means its value never changes. However, its numerical value can change based on units of pressure being used in the problem. That seems like contradictory at first. Here I'm saying that the value of R doesn't change. So I try to think of an example that I could give to you that would relate this and make it sink in with you. At first glance, are the numbers 1, 0.33, a third, and 12 equal? And of course, you'd say at first, no, they're not equal. But what if I add 1 foot, a third of a yard, and 12 inches? If I now said to you, are those equal? You would probably reply, yes. So here is something, a foot, which doesn't really change. It's the same length, but depending on the units we measured it with, the actual number could be different. So does 1 equal 12? Well, yes, if you're talking about 1 foot compared to 12 inches. So the gas constant R must be thought of in a similar fashion. If we use different units to measure pressure, then we're going to have different values of R. So here is an example. If we are using the gas laws, the ideal gas law, we're solving a problem, and they give us the pressure in kilopascals, we're going to use the value of R of 8.31. Now this looks intimidating, but all this stands for is kPa are units for pressure, liters are units for volume, moles is obviously units for moles, and K is going to represent temperature. And these units will all factor out, leaving behind the one that you're solving for, and problems will work out with you here in a little bit. Now, if we're given a problem to solve using the ideal gas law and they give us pressure in atmospheres, well, then we have to use 0.0821. So the question is, are 8.31 and 0.0821 equal? Yeah, in a similar fashion, the way 1 foot can equal 12 inches. If we have units of kilopascals, we must use 8.31 for the value of R. If the problem is given to us with units of atmosphere for pressure, then we have to use this value for R. When you're using the ideal gas equation, it's important that you remember that the units for volume must be liters and the units for Kelvin or the units for temperature must be. Got to keep that in mind. Let's scroll down. Something else I need to talk to you about. Since temperature and air pressure varies from place to place A standard reference is necessary for comparing and testing the documentation of chemical and physical processes. Basically, in chemistry for gas laws, we have standard conditions. They call it STP. Standard temperature is defined as 0 degrees Celsius. Standard pressure is 1 atmosphere. So if one scientist is talking to another scientist, say, hey, I'm studying this gas at standard conditions, that scientist knows that they mean 0 degrees and 1 atmosphere. All right, next I thought I would go through and work out a couple problems with you, showing you how we can apply the idea. Okay, here's an example problem using the ideal gas law. It says calculate the volume occupied by 1 mole of a gas at STP conditions. So we need to recall that STP conditions means 0 degrees Celsius, which is the same as 273 K. We're going to have to use K because this is a gas law, and 1 atmosphere. So the ideal gas equation is PV equals nRT. So I simply plugged in for pressure, 1 atmosphere. Volume is what we're solving for. We have 1 mole, so I put that in for N, which stands for moles. The value of R is 0.0821 because the pressure is given in atmospheres. And temperature is 273 K. I solve, and I end up getting an answer of 22.4 liters. That means the volume of 1 mole of a gas at STP conditions is 22.4 liters. This number is significant and is going to be very helpful for us next week when we go back to doing stoichiometry involving gases. So no matter what the gas is, if that gas is at STP conditions, 1 mole of it is going to always occupy 22.4 liters, always. Again, I repeat, 1 mole of any gas at STP conditions will occupy 22.4 liters. You're like, well, how is that useful? Let me give you a quick sneak preview. What if you had 44.8 liters of a gas at STP conditions? Well, if 1 mole occupies 22.4, and you have 44.8, then you must have 2 moles of gas. So this is going to become useful again later on this week, and we'll come back to that. The official definition from our textbook, molar volume is defined as the volume occupied by 1 mole of a gas at standard temperature and pressure conditions. So this is important to remember. So kind of write that down in your notebook somewhere and hold on to that. And we'll be coming back to that, like I said, later on this week. Let's try another problem. Okay, here's a second example. What must be the volume occupied by 0.6898 moles of chlorine gas at a pressure of 1.89 atmospheres and a temperature of 36.9 degrees Celsius? Well, the first thing I want to draw your attention to is you've got to look at units of pressure because that's going to tell us which value of R we need to use in the problem. So in this case, we're given atmospheres. That tells us we're going to once again use 0.0821 because that is a number associated with atmospheres. The second thing you got to be wary of is that the temperature is given to us in Celsius. Celsius is no good for gas laws. So we have to convert Celsius to Kelvin. So now we have the correct value for R. We've converted temperature to degrees or to Kelvin. We now have to go ahead and solve for V. So we plug in. Pressure is given as 1.89 atmospheres. Solving for volume, we are given 0.698 moles. I put the unit or R here. Don't let the units confuse you. It's just a label. I'm going to show you how they cancel out. And there's our units for temperature, 313.9 Kelvin. So when we multiply all of these numbers together on the right side of the equation, moles is in the denominator, so moles is going to cancel. And then K and K are going to cancel, leaving us atmospheres per liter on this side. So 0.698 times 0.0821 times 313.9 is equal to 18. On the left side, we still have the 1.89 atmospheres times V. When I go to divide both sides by 1.89 atmospheres, the units of atmospheres will cancel, leaving me with liters, which is the correct units for volume, and we get an answer of 9.52 liters. So once again, we're just kind of doing simple algebra. The tough part about these is make sure that you have the right units for everything involved. All the variables must have the correct units. Quick reminder, N is moles, so if they give you grams, we got to convert to moles. Temperature's always got to be in Kelvin. Volume always has to be in liters. And then R is going to be dictated by what unit of pressure you're working with in the problem. The labels and units here can make this look a little bit more difficult, so I thought I'd work it out with you without the units, just to try and show you that we're not doing too difficult a level of math here. So there's the equation without all the labels and units. So to solve this, we would simply take 0.698 times 0.0821 times 313.9, and that gives 18. Watching my sig figs, 3 sig figs here, that's a given. That won't control our sig figs. So we have 1.89 times V equals 18. And like you would do in Algebra 1, to isolate that variable, we're going to divide by 1.89, and I get an answer of 9.52. So these two are showing the same thing. This one just has all the labels and units associated with it. I'm just trying to show you that the math really isn't too difficult, so don't let that intimidate you. All right, I had one more that I worked out, and I'll share with you, and hopefully you'll be ready to get going on the Google form I'll be posting here. Okay, here's the third one. How many grams, so that's what we're looking for, of oxygen are present in a 368.2 milliliter sample at a temperature of 21.8 degrees and a pressure of 105.6? So we're looking for grams. And your first thought is, well, wait a minute, the grams is not mentioned in the equation anywhere. And you're correct, it's not. But N stands for moles. So if we solve for moles, we can then convert moles to grams and come up with the answer that they asked for. So that's not going to be a big problem. I just want to make sure I draw to your attention the problem, we're giving volume in milliliters. Now remember, it must be in liters because that's what the units of R are. So I showed you here to simply convert to milliliters to liters, we just divide by 1,000. The other thing you have to remember is temperature's got to be in Kelvin. Celsius can never be used in the gas laws. Never, ever, ever. So I converted that to Kelvin. So 21.8 degrees Celsius is equal to 294.8 Kelvin. So I plug in. Go back and gather your numbers. Be careful because this is where people make mistakes. They get in a bit of a rush. 105.6 is pressure. So I put 105.6 in for the pressure. The volume I had to convert to liters as shown up here. It's 0.3682, so I put that right here for the volume. We're solving for N. Now notice R is different than the previous two problems. The reason R is different is because we were given pressure this time in kilopascals. So the value of R when pressure is in kilopascals is 8.31. I plugged in 294.8 in for temperature, and I have that right here. I did the math. I took 8.31 times 294.8. I'm allowed to have 4 sig figs. That's why I put that decimal point there. That means the 0 is significant. This does not control our sig figs. It's a given. That controls our sig figs. On the left side, I took 105.6 times 0.3682, and I came up with 38.88. Again, being mindful of the sig figs. When we multiplied these two values over here, you can see that the units are going to cancel. To solve now, I'm simply going to isolate N by dividing both sides by 2450. When I do so, kilopascals and liters cancel out and I'm left with moles. So the answer is 0.01587 moles. That 0 is not significant. So we're almost done, but we have to remember it didn't ask for moles. It said how many grams. So the question asked for grams, so we need to convert moles to grams, which you're all like probably doing your sleep by now. So here we go. I take the 0.01587 moles. It's oxygen. On the stoichiometry part, some of you still forgot that oxygen is one of the diatomics. Remember, there are 7 of them. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. They're all diatomic. So since oxygen is diatomic, its molar mass is going to be 32, not 16. So we convert moles to grams. I watch my sig figs. Placeholder 4 sig figs. Does not control my sig figs. My answer is 0.5078 grams. That's it. So that is how you apply the ideal gas law. I'm going to post a Google form, and they'll have a worksheet. Then we have to talk about the density of gas, and we're ready for another assessment. So far, like I said, I'm very impressed with the work that you're doing, and I hope you're learning a lot. And if you have any questions as you go through the work, you always can email me or you can ask me questions during Google Hangouts during my office hours. Okay, everybody, take care.